Today we're going to talk about how there is no scientific method.
Welcome to Missing the Mark, where we look for meaning in strange places. I'm Christopher.
So when I say there is no scientific method, I'm referring to that thing, you often learn it in school, where it goes something to the effect of like, here's the scientific method. Step 1, you make observations. Step 2, you form a hypothesis. Step 3, you design an experiment. Step 4, you execute it and collect the data. Step 5, you evaluate the thing, the hypothesis, and then either throw it out or refine it based upon your observations, then go back to it. And there isn't really an end state except like at some point no one can form new experiments, so we're going to consider this essentially true. Okay, so one of two things, depending on really exactly what you mean by this. This is either just describing the basic act of human cognition on all subjects that everyone's done over basically all time, or alternatively, this isn't what scientists do, this isn't what people use, and this isn't really anything. So there are several different, we're going to have to unpack this because there are a few different things that relate to this. So to start off with, to a great degree, this is just basic human cognition. Like, you want to know how something works, well, you look at it, and you think about how it works, and then you poke it or prod it or gather more data or look more closely at some aspect of it to see whether or not you're right. And this is like on the basis, like let's say you want to hunt deer, right? You think like, there are deer footprints here. Maybe that means deer come through here, like more than just once in the grand history of the world, because who cares if they came through here before but never do it again? Maybe this means there are deer here. Let's look around. Oh, look, there's a deer food source. That would make sense with there being deer here, because deer like to go to food. And where could they be bedding down around here? Because deer like to bed down. Okay, there's some cover over there, and here's the more exposed food source, and there are deer prints in between those two, so it makes sense that maybe they bed down there and come over here. Now, if they go back, though, rather than just were here once, I'd probably see footprints going in both directions. Is the ground the sort of ground that can have footprints? Let me see. Oh, look, yep, I see prints going that way, too. So yeah, maybe they bed down over there and come back and forth. So I think it's worth me setting up in, a bluff, a hide of some kind, climb up that tree, hide behind the stuff, whatever. Wait here with my bow and arrow for the deer to come through for food tonight. Hey, I just did the scientific method. And this is literally how you go about something like hunting. People have been doing this since before there was written language. This is not a revolutionary thing. This is not some specialized method. There isn't some other way people do things. People who want to actually achieve a result don't just go like, I'm going to just make some stuff up and that's good enough. There are deer over there. I'm going to now set up over there with my hunting equipment and just wait there because I'm convinced there are deer there because who needs a why? That's not how people work. No one's ever worked that way. The idea that there's some specialized thing that consists of, in order to find out if something's true, I'm going to see if it's true, get an idea of what's going on, and then, try to see, figure out ways of testing my idea to see whether or not it's true or false. That's how people think. There's nothing new about that. There's nothing special about that. There's nothing particular to science about that in any way, shape, or form. Now, what this is sometimes confused with, and I don't know really the history of this idea that there's a scientific method that was part of the scientific revolution. There wasn't really a scientific revolution either. That's the thing. If you actually look at the history of science, natural science, and natural philosophy, which later got called science just from scientia, Latin for knowledge, it's actually, the history of science is about 99% the history of the improvement of the ability to measure things. So look at the Copernican revolution, right? So who was it who wanted, in a nutshell, who was it who wanted to be able to actually predict the motion of the stars? Astrologers, right? And people have been doing astrology to predict the future here on Earth for millennia. And so there's a really good model developed by Ptolemy, which was actually highly accurate and did an excellent job of predicting where the planets would be so that astrologers could cast their horoscopes. The other reason is it helps you to keep track of time and seasons and stuff. And it worked great for that too. advance, like essentially 2 millennia from when Ptolemy did this, and one of the problems that you get is copying down tables of numbers is something human beings are really bad at, because like it's doesn't have any inherent structure that helps to check whether or not you got it right. Whereas when you copy down language, there's a structure to language, there's redundancy that's built in, such that like when you're copying it down, if you get the word wrong, it'll feel wrong because it doesn't match with the rest of what's down there. Copying down tables of numbers is not like that. And when copying was by hand, over the course of 2 millennia, enough copying errors crept in that the Ptolemaic model wasn't working so well because the data that you fed into it was wrong now. It used to be correct and now it's wrong. And so you put in bad numbers into a good model and out comes bad results. And so there are various things that were going on to try to solve this problem. But, people didn't really know that at the time. So we're talking, roughly speaking, 1400s, 1500s, approximately the time of Galileo. And so one thing some people are doing is actually going back and making, retaking basic observations. But another thing is people are thinking like, well, this isn't really predicting very well. Maybe the model's wrong. Turns out, incidentally, it wasn't that the model was wrong. See my video on models. Like all models are wrong, some models are useful. The Ptolemaic model was actually a useful model. It could predict good things if you put good input data into it. But since people didn't know where the problem was, they thought maybe the problem was in the model. And so what they did is, and so there are various attempts to fix this. But what happened at approximately this time was that you had, people had been doing lenses, like glass lenses, for things like to help people see, since about the 1200s. And it didn't take that long before people figured out, okay, if we do this and exaggerate it a lot and then correct it, basically like if you can have a big lens that concentrates things down and corrects it. So you need 2 lenses. And if you do 2 lenses, as they start to understand how the lenses worked, because the thing is, glasses, the second lens is actually literally the lens of your eye. So the glasses, when they're like magnifying or what have you, the second lens in that system is actually the lens of your eye. Whereas in a telescope, what you want is the second lens to be, have a second lens so that you can have a bit of eye relief from it for various reasons. Anyway, they developed the 2 lenses and were able to see things very far away. And this is happening right around the time of Galileo, where people start developing lenses in ways where you can mount 2 of them. And the original telescopes actually didn't have the light rejecting tube around them. So you just had the 2 lenses, so they weren't as good as later on lenses, and nowhere near as good as mirror lenses for various reasons that I won't get into. But anyway, this enabled you to see things much further. There's an interesting thing. I think Galileo was showing somebody where they looked across a river and into somebody's house, and the bishop he was showing it to was astonished, like, wow, it's like you're practically in the room with them. This is amazing. Never before had people been able to observe faraway things any better than they could see with the naked eye until the invention of the telescope. Why did Galileo discover all those moons of Jupiter? It's because he could see things that you can't see with the naked eye now, because he had one of the very first telescopes that anybody had. He wasn't the only one, and there were a bunch of people discovering things at plus or minus the same time, and so on. Anyway, point being, once they could see much more clearly, once they could observe things with much greater detail, once they get much better positioning, once they could see what stuff was around, it gave them so much more information that they could then use to make better theories. And then this is where, because they were exploring other models, that's where the Copernican model came in. And then what's really funny about the Copernican model was that it was actually, I won't get into this, there's a really fascinating set of blog posts on topspot.blogspot.com. It's called The Great Ptolemaic Smackdown, Ptolemaic and Ptolemaic. It's a fairly detailed history of this. And one of the fascinating things was that there's some pretty big problems with the Earth moving that have to do with things like parallax. And if the Earth is moving, we should, especially upon the telescopes that existed at the time, we should be observing vastly more, the stars would either have to be unreasonably large, like wildly bigger than our solar system, or crazily, the problem was the stars would have to be crazily far away in order to observe the parallax that we were seeing. And it turns out they are that far away, but that contradicts the fact that the disk that you see would make them ludicrously large, like stars wildly bigger than our solar system at the distances we see they have to be at for the parallax to work, given how big they look when you look through them, which turns out to be an artifact of looking through a lens. And this is why mirrors, which don't have that problem, lenses produce an apparent disk, whereas mirrors don't produce that apparent disk. And it was only like 150 years later that this was actually figured out when mirror telescopes were developed, or 200 years later, something like that. With the advent of mirror telescopes, that the problem of the stars having to be unreasonably large was finally resolved, such that you could say, like, okay, so the Earth is moving, and the stars are just crazy far away, and that's why we don't see the parallax we should be seeing if the Earth is in fact moving. The funny thing that people generally don't get taught is how, in fact, like the Earth moving was contradicted a lot of evidence that scientific evidence that people had at the time. And in fact, it wasn't a really great scientific theory in many ways, because it directly contradicted evidence that there wasn't a good explanation for. Like, the stars are crazy large, obviously radically different than our star. They're not the same thing. Radically huge things that would have to like collapse into, and not that they knew it at the time, because black holes are only a 19th century thing, but things so big their gravity would cause them to collapse into black holes now. Anyway, the point is, that was all about the improvement in the data that was collected, which enabled you to do things with much greater precision, which enabled you to look at stuff and figure things out. There are some problems where, to some degree, the model was accepted, even though it contradicted evidence, because it produced such really good results. And to some degree, since at the time, all anyone really much cared about was casting horoscopes, and the Copernican model did a much better job of predicting stuff than the Ptolemaic model with really old observations of like exactly when things show up and their exact angles and other things like that. The data that you plug into the model, well, the Copernican model was accepted because it produced better results. And then eventually we figured out ways of explaining around the problem with how the Copernican model contradicts, basic common sense and the scientific evidence available at the time. Okay, so that's a good example. A lot of other places too, where the ability to measure things precisely depend upon things like material science at the time, the ability to produce really good, like steels that could withstand certain pressures, to be able to manufacture things of very particular distances, of very particular thicknesses, and so on. Like, for example, like if you ever look up the experiment like the milk and oil drop experiment, for example, the one that gives you the charge of an electron. If you ever look that up, you spray oil droplets that get I forget which sort of charge you get, and you set up two electric plates that generate a magnetic field between them, and then what happens is you get most of the droplets will either get pushed up or fall down, but ones of an exactly right size for the field get suspended, and then what you do is you turn off the field, let them drop, measure the speed at which they drop, and then from there you can compute the mass of the thing, because you take into account air resistance, etc. Do this a whole lot of times, and then you find that every single one of the charges of the droplets, so you can, with the plates you have the known charge, and then with a known mass you can compute, and it turns out that every single one of the charges of the droplets is a multiple of some constant, which must be the charge of the electron. Yeah, well, until you have things like electric sources that can produce charged plates to have a magnetic field you can turn on and off at will, good luck running that experiment. Now, this, by the way, was the milk and oil drop experiment, was the experiment in measuring the charge of the electron that actually produced something like reasonable proof that electrons even existed. So good luck pushing your scientific theory that electrons exist before you can technologically demonstrate that the things even exist. And on and on and on. Look throughout the history of science. There are most of the time, by the way, technology actually predates the science, and science explains how the technology works. The major exception I can think of there are the atomic bomb and and radio. They're the two really big ones that come to mind. Radio was predicted by Maxwell because of his theories of electromagnetic radiation. And then people tested to see if it was there and then discovered it. And then the atomic bomb, obviously, that one's probably better known these days. Most of the time you have technology predating it. In any event, what you always have predating science that is in any way useful, or science that is in any way testable, is the ability to measure accurately in a way that people were not able to measure accurately before. And if you actually read the specific histories, whether you're talking about the milk and oil drop experiment, or whatever it is, what you tend to find is they're using things that were developed in the last 10 to 20 years. They're using things that did not exist that much longer beforehand. And so why are they the first people to discover something? Most of the time, Maxwell possibly being an exception here, and the nuclear bomb too, most of the time it's because people had the ability to measure things. It just recently gained the ability to measure things. So who is it who makes the discoveries? It's the first people who use the technology that gives you the ability to measure things no one had ever been able to measure before. So it's not, if you look at it, that there was and so the other part, philosophically speaking, the scientific revolution was in large part, the way it's largely regarded in the philosophy of science is a move from natural philosophy to science, or scientia. It was a retrenchment, a backing up into only considering mathematical models, only looking at what can be mathematically described and therefore related. But what does that really mean? That means it's only looking at things that can be measured. And it's with the advent of the ability to measure things precisely that you get this retrenchment to, we don't really know what's going on, but we can measure it with phenomenal precision. And so we're going to do that and come up with models of the things and then check these models against what we can measure, because we can actually do that now. We have these amazing measuring devices, so we're going to just focus on that. We don't know what's really going on. It doesn't really make a lot of sense, but who cares? We can measure, and that's a lot more than nothing. Well, there's nothing special about that. That wasn't like a great insight that people had been refusing to measure things before until they had complete holistic models. They didn't have the measuring devices before. It's not like people in the 12th century refused to measure the charge of an electron because they did not, have a philosophical model of what an electron really is. And so why would you measure its charge if you don't have a philosophical... They couldn't measure the charge. That's why they didn't measure the charge. That's it. I mean, the people involved, the individuals are clever and stuff. It's the cleverest people who figure out how to use newly made technology to do things. It's not like idiots who use new technology. It's always very clever people. So I'm not trying to take away from them. But if you look at it, they always are using new technology that hadn't really existed, any great length of time beforehand. They're always relying on material science. Frequently it's material science. It's the ability to, balance stuff that, the ability to balance things with phenomenal precision, the ability to make long things of exact lengths and measure exactly how big they are and come up with the exact masses of what you have, and various stuff like this. And, for example, the experiment that showed the gravitational constant. It's a really, really clever one. It uses a torsional balance, which is basically, conceptually speaking, it's a super thin spring, a elongated spring, that when you twist it, it will get very slightly shorter. And the more you twist it, the more resistance you get to twisting, because it's very slightly shortening. In theory, you can use something like a strand of horsehair, except the torsion balance used here, it's like an 8-foot long rod on the torsion balance with, with like 8-pound weights on both sides. So, you've got something that's holding like 16 pounds or so through a phenomenally thin little thing being held. And then you could rotate next to this thing, these 200-pound or 200-kilogram, I forget, weights. And what would happen is their gravitational attraction was sufficient to overcome the insanely tiny amount of force necessary to twist the torsion balance a bit. And then there are various ways you compute the actual resistance to twisting of the torsion balance itself, and with the mass is known, you can compute how much force is being applied. Now, the problem is it's a lot less than the force of air currents. So, very cleverly, the guy built this in a shed, where he just had like viewports and clever ways of being able to measure it without being able to interact with the air inside, because like light breezes would massively overpower the gravitational attraction of a 200 kilogram weight to like a 4 kilogram weight. So it's really, really clever, but it's a technological invention. The technology to do a torsion balance, to some degree, is the first person who came up with the torsion balance, is the first person who measured gravitational attraction. It was a new piece of technology, because the question was like, okay, how do we measure forces that are insanely small? And they really are like just crazy, out of this world forces, so minor you can't feel them. Can't even begin to feel them, can't come close to feeling them. Forces so small they couldn't pick up a feather. How do you measure a force that freaking tiny? And so somebody came up with this really clever invention for how you do this thing. And once that technology actually existed, then people used it to measure things. And there's actually a lot of stuff that people have used scientifically in torsion balances, and great stuff have come from it. But it was the invention of the torsion balance. And before this, which they were really hard to set up, until that technology existed, you couldn't use it. And so that's the thing. And look through the history of science, and you'll find this over and over again, that the history of science is largely the history of technology that then gets used to do science. And it's not that there was some great intellectual change. It's not, contrary to essentially propaganda of the Enlightenment, which is a propagandistic name. Contrary to that propaganda, there wasn't some like radical change in thinking that unleashed human creativity. There was the ability to measure things in a way people had not been able to measure before. Because very rapidly with lenses, you develop two things. You develop telescopes and you develop microscopes. And these two things enable people to make observations that no one had been able to do. Like with glass, it took a while to get to like 1,000 times magnification. But with a lens, glass lens, you make it really well, you can get up to the sort of magnification where you can actually see cells and kind of see inside of cells. And if you don't have that, cells make no sense. But when you can see them, now, wow, can you like really start to understand how the body works? Because you can see these things that you couldn't see before. And prior to the existence of that technology, you couldn't. It wasn't a intellectual revolution that enabled people to think thoughts no one had thought before. It was a technological revolution that enabled people to measure things they'd never been able to measure before. And then these things snowball, because like as you can measure real precisely, you can make things that then enable you to measure other things even more precisely, and you can get finer and finer tolerances on your devices that then enable you to get even finer tolerances to measure things better. And you get a snowballing progression of precision. Because like back in the day where the way you make iron, an iron thing is you just heat it up and you whack it with a hammer until it's basically the right shape. And like, how do you know if it's the right thickness? It's like, well, you hold the two thing, like whatever thing you want up next to it and see if it's thicker or thinner or whatever. And that's the best you can do. But like, add in that you can then use something like a microscope to figure out whether or not it's at exactly the right distance. And, because you can blow up, you can see things you wouldn't be able to see because they're too small, to now get really, really good precision. Do things like have two things that really fit exactly next to each other, rather than like leak a bunch of gas in between them or rub too much on each other. Like if you're doing a gas piston because you want to do volume measurements or something like that. All these things get enabled in snowball and enable you to make all sorts of better things, and you get better metals that can withstand higher pressures that allow you to provide more force on things, and on and on. All of this stuff snowballs. And that snowballing effect, the fact that better technology enables you to make even better technology, is kind of why did technology kind of like go like that? It's not because like there was some point where people were like, wow, let's actually start thinking. It's because as technology gets better, it enables you to get better. And like look up the history of steel, and like, steels kept getting better. Look up the history of metals. For those who don't know, the way you make metals is you take various ores out of the ground where mostly it's like the metals are bound into oxygen, whether it's copper or iron or whatever. And then you heat them up to tremendous temperature with something that oxygen will preferentially bond into. Once you've heated up so hot, the oxygen splits off from the metal. It'll then preferentially bond into something else that it bonds better to. And you're left, as long as you're in an anaerobic environment, with with the refined metal. Well, and the very first metals that people did this with were really soft metals, pardon, with really low melting points, and they weren't very good. But this is where, you may have heard after the Stone Age comes the Bronze Age. Well, bronze was not the first metal by any means. Like, you had copper beforehand, which wasn't very good, and you have tin, which was even worse. Tin's not a very useful metal. Like, you can make plates out of it or something. Really low melting point, very workable, very soft, not good for, not as good as stone for weapons in many ways. But you mix copper and tin, and you get bronze. I'm pretty sure that's bronze. Copper and tin is bronze, and copper and nickel is brass. I forget now. Anyway, if I'm getting the particular alloys wrong, I apologize. I know it's bronze is copper and something, and I think it's tin. And bronze has much better characteristics. It's very workable, but it can be hardened in very useful ways, and it makes some really great tools. And so, like, that in itself is a progression of materials science as you start figuring out how to make alloys that work a lot better. And then people got iron. And then in the Iron Age, people start figuring out how to, like, work carbon and get steel. And steels, oh, the complexity there is truly amazing. Steels are a fascinating subject, just as a side note there. But the thing is, because, like, sometimes it's like, people figure out things like how to quench things, where you heat them up really hot and cool them down super fast. And then you get something incredibly hard, but it'll shatter. And so you have to temper it, where you heat it up again, but not as hot, and you let it cool down slower. And so this way you take some of the hardness off. And so you get a good balance of where it's hard and, pretty hard, but not so hard it'll shatter. This changes the crystalline structures of the steel. And then, like, the particular things that you alloy into the steel can do amazing stuff. And so the history of steel is fascinating, but, like, as it progresses, you're able to do all sorts of things. And, like, you could not have the steam age back in the Bronze Age. It doesn't matter if you have the idea of a steam engine, you can't develop enough pressure in something sufficiently small and lightweight to do anything useful with it. It's really only when you get, and so, like, during the Middle Ages, steel especially in Europe, steel kept getting better and better and better. You had Bloomery steels, and then you had, blast furnace steels, where you get all sorts of really great characteristics in them, and then you alloy them with stuff, and you got some phenomenal, by the time you're getting to the 1800s, you have some phenomenal steels in comparison to, like, early iron, which can do all sorts of amazing things. They're so much stronger and longer lasting and better against the sort of stresses you're putting them under and so on. And then, around the 1800s, you finally have steels that are practical for making things like steam engines, where the steam engine is light enough that it can generate so much power it can pull a bunch of other heavy things. And fun fact, for example, the original railroads, Lindy Beige has a great video on this, by the way, the first railroad, which predated the steam engine by, like, over 100 years, where it was very specific thing. You had pretty flat ground, and you needed to get massive amounts of coal over to boats on fairly flat ground. And it turned out that building wooden rails to put your wagons on could improve the ability to pull this stuff along tremendously, where their profits shot up like 5 or 10-fold, something like that. I forget the video. Look up the video. It's a great video on the history of this. It's in England. And so the railroads, the steam-powered railroads, were like 100 years later after railroads, where you finally had these steam engines that were just way better than horses, but horses were still great for pulling these things. And the ability to measure pressure, and because, science and technology are so often related, but, like, the ability to, move large quantities of stuff, the ability to, enables you to make all sorts of experiments that are hard to make before. As you get things like good quality steels becoming cheaper and cheaper, you can do all sorts of pressure volume experiments on that kind of stuff, because you now can afford to have high precision metalwork that's light enough to actually move stuff around. Because, you can make, as early cannons show, like, you can make a steel tube that'll hold insane amounts of pressure if you just make the thing unbelievably thick. Now, the problem with the cannon wall that's this thick, of course, is that you can't move the darn thing. It's so incredibly heavy because it's this thick, all the way around. That you ram the gunpowder in, ram the cannonball down, and touch it off, and boom, that's great. But how do you get this thing to where you want to actually shoot it? Because it's so darn heavy, and only with better steels it can be much thinner and therefore a lot more transportable does this really become useful. Same kind of thing applies though to other stuff. And scientists always have a budget. So as technology enabled things to get cheaper, a lot more experiments came within the range of what a scientist who wanted to do it could afford to do. So again, all of this, there isn't some scientific method that enables you to do science that people didn't have until they discovered the scientific method. The scientific method is just thinking, quasi-formalized. What really happened was the snowballing of technology that enabled people to measure things they'd never been able to measure before, to make machines that they've never been able to make before. Because, by the way, there's a related subject that a lot of people get wrong. A lot of people will try to say that, I'll only believe what I can perceive with my senses. I'll only believe empirically verifiable things. And empirically verifiable means verifiable through your senses. But the problem is your senses can verify extremely little. And so you then have to add in, okay, through my senses or through mechanical aids to my senses. I'm going to count it if I look through a telescope and see it, even though I can't see it myself, and I'm trusting that the telescope is actually just showing me what's on the other end of it. Small field of view, much bigger. So there's a non-empirical step where you're trusting that the telescope is actually doing what it's supposed to do, and so the thing that you see in the telescope is actually what's out there. It's actually not empiricism, but it's the modified form of empiricism most people will admit. But the thing is, telescopes and microscopes don't take you very far, and there are lots of other things that people use, lots of other machines. If you want to measure the pressure of a gas, okay, that's putting your hand on something. Other than that, you're using a machine where you're trusting the machine to give you a reading that is actually what's going on inside. You're essentially trusting the testimony of the machine. Now, I can almost hear the angry atheists who are going to be shouting about, oh, but you can verify. Yeah, but you don't. You don't actually verify it. A few people do, and one of the big things in science is most people don't. Nobody, it's very rare for people to repeat other people's experiments. Nobody has access to and you have to do that because otherwise you don't have access to other people's equipment to verify that they actually calibrated it correctly. So there's lots of stuff, but there's a reason why all sorts of things get shown to be false and get retracted and so on, often a while later. And it's not because they got caught right at the very beginning. Anyway, point being, the problem with this kind of empiricism is that pretty quickly you run out of things you can empirically verify, and so you can actually verify with your senses, and so you have to trust machines to do this. And you can't do that stuff until you have the machines that you're using. Until you have a scanning electron microscope, you can't look at structures that you're too small to see with about 1,000 times magnification light microscope. Lenses don't really work much past there. They don't work right for what you're trying to do with them. And so you now have the scanning electron microscope, but that requires a ton of theory in terms of what's actually going on. If you really want to see a great one, take a look at how the discovery of particles in cloud chambers in the magnetic accelerators, cyclotrons and I forget the generic term for them. Anyway, but the big atom smashers, where they have lots of magnets and impart crazy amounts of energy into particles and slam them into each other, and then they measure exactly what happens in the cloud chamber where the things smash into each other over the course of femtoseconds, and then they record crazy amounts of data and then do statistical processing. And the way a particle is defined to be found is if you register things that correspond to particles of certain sizes with a certain, often enough that the odds of measuring, having these measurements without the particle by statistical chance is at least 5 nines, 99.99999% likely that this is not caused by chance, then hey, we found a particle. And the amount of argumentation the amount of explanation required to like even figure out what's going on is quite extensive. The amount of argumentation required to like convince a person that this is actually all valid, that like the way this thing works and the algorithms that they're applying to and so on is really quite huge. And this has nothing whatever to do with empirical verification, because you are making one heck of a statistical argument at this point, which is not empiricism. So this is the thing. When you put it all together, they're either the scientific method is just describing the basic act of human cognition, or there is no scientific method. By the way, the other thing is, like, different scientists do different kinds of things. And so, like, biologists who go out into the field and collect beetles and look at them and describe them clearly, they're not doing a scientific method. They're not forming hypotheses. Unless you want to do some stupid thing like, my hypothesis is that this is a beetle. Or my hypothesis is that this is a different beetle than all the other ones. And I'm predicting it will have different traits if it's not the same species of beetle. Hey, look, it's got a different trait. No one's doing that. That's stupid. Like to try to apply it that way is just dumb. So like that's another thing. Plenty of scientists just take observations. They're just doing observations like, this thing exists. End of story. Like, you've taken observations and you're done. There's no theorizing that goes on. There's no theory and experimentation to test your hypothesis. You just take observations, and that was the scientific discovery, is to observe a thing. Like, that's a great deal of science. It's just straight up observations, and you don't theorize after that. You just have the observations. You like know what sorts of things actually exist because you have went and found them. That's a big part of science, and also not related to that whole scientific method thing. So plus you have plenty of scientists who just say things like consensus opinion is science. Lots of people will tell you this in various fields, that the consensus opinion. You will find people who will desperately try to argue that paleontologists conduct experimentation, but no, they don't. They don't do anything like that. You don't have verification of theories. No, I mean, okay, there's an asterisk. When you find like 3 bones and hypothesize what the entire animal looked like, yeah, okay. At that point, then at some point you hope you dig up more bones and find out whether or not you were correct. But like, you're not really testing a theory at that point, because like you're not gaining some things that either confirm or disprove the hypothesis. You're like finding out the answer. Like when you get more bones, like you find a complete skeleton, now you have the answer. You're not like testing a theory or anything. You just got the answer. So, there's no such thing as the scientific method, or alternatively, it's just thinking, and people have been doing it since the dawn of thought. Until next time, may you hit everything you aim at. If you like this video, then clicking the like button, according to YouTube, will make them more likely to recommend it to others. If you know anyone who might get something out of this video, then it would be kind to share it with them, or just share it on social media in general. And if you'd like to see future videos of mine, you can subscribe. And if you're not in the habit of checking your subscriptions page regularly, then I suggest clicking the notification bell and setting that to always, because otherwise subscribing to a channel basically just sort of like gives YouTube a hint that maybe it should consider recommending these videos to you, possibly at some point, if they think so. It's a funny world we live in. God bless.